Hello again. We're going to be talking about time in Markov cohort simulations a bit more, but this time talking about how to choose the right cycle length for your model. In a Markov model, the cycle is the unit of time in your health economic Markov model. It's a fundamental assumption of your Markov model that it's not possible to transition more than once in a cycle. So if you recall the illness-death models that we've looked at in the past, with 3 health states, healthy, diseased, and dead, it is assumed to be impossible to die of the disease in the same cycle as you are diagnosed or develop the disease. How believable this is depends on the cycle length. If the cycle length is 1 day, this is a very believable assumption. However, if the cycle length is 1 year, that's not very believable. You might wonder, why don't we always just make the cycle length really short, for example 1 day? The problem is that each additional cycle in a model is a bit more work for the computer, so it will take a bit longer to run. If we halve the cycle length, we're going to double the number of cycles, so there is twice as much work for the computer to do. That's why we typically have models with on the order of 50 to 500 cycles. If our model has tunnel states, then we also need to double the number of tunnel states if we halve the cycle length. That can potentially quadruple the amount of work and the time to run the model. In chemotherapy models, it's common to have the model cycle length be equal to the chemotherapy cycle length, or any other treatment schedule for similar diseases. This makes it easier to calculate the cost per cycle, because the model and the chemotherapy cycles are synchronized. I've got some rules of thumb here that you might find helpful. It's difficult really to ever justify a cycle length over 12 months. A 12-month cycle length is frequently used, but it's probably unsuitable in most cases. A 3-month cycle length is often good for chronic conditions, whereas a cycle length of 1 week to 1 month, or perhaps even shorter, is better for acute conditions. You should aim to keep the probability of remaining in a health state each cycle over 0.95, so less than a 1 in 20 chance of leaving a health state each cycle. Try to keep the products of the probabilities of transitioning to other states close to 0. Check that it's reasonable to assume a constant hazard rate within a time cycle. For example, if you know that the risk of dying from something increases sharply over time, then it might not be reasonable to have a cycle length of a year. And crucially, if reducing the cycle length further makes a difference, you should do it. Here I've got a bit of an example. It's got some maths in it, so don't worry if you skip over this bit or don't fully understand it. But we let lambda1 and lambda2 denote the hazard rates of 2 independent competing risks in a particular health state. So, for example, in our illness-death model, when you're in the healthy state, there are 2 competing risks that can take you out of that health state. One is that you transition to the diseased state, and the other is you transition to the dead state. These compete against each other because as soon as you've left the state, you're no longer at risk of leaving the state. When we calculate our probabilities from those hazard rates, we have the option to account for the competing risks or ignore them. So if we ignore that these competing risks exist, we would calculate the following probabilities. So the probability of succumbing to the first risk with lambda 1 would be 1 minus e to the power of negative lambda 1 times delta t, where delta t is the cycle length. The probability of succumbing to risk 2 is the same formula, but substituting lambda 2 for lambda 1. And then the probability of succumbing to neither risk would be e to the negative lambda 1 delta t plus e to the negative lambda 2 delta t minus 1. The formulae are slightly different when we include the competing risks, and these are the correct ways to calculate these things. But as we'll show, it doesn't matter too much so long as delta t is appropriately chosen. So here are the formulae for succumbing to either of the risks when you do include competing risks. The way that it's best to look at this is to look at the probability of succumbing to neither risk. This is a fairly simple formula. It's just like the probability of not succumbing to one risk, except instead of a single hazard rate, we've added together the two hazard rates. So lambda1 plus lambda2 are added together, so it's the risk of a composite event happening. And then if you take 1 minus that, then that's obviously the probability of succumbing to a risk, and then which one of those depends on the relative magnitude of the rates. So that explains the two equations above those. Now, the extent to which these methods will give you different results depends on the values of those hazard rates and the cycle length. Here we've got an example where I randomly chose a bunch of different hazard rates and then put them into a model with different cycle lengths. So in the purple, we have a cycle length of 1, so like 1 year, going all the way down to a cycle length of 1/12, so like 1 month in red. On the x-axis, we have the correctly calculated probability of remaining in the state in which we account for the competing risks. And on the y-axis, we have the probability of remaining in the state when we don't calculate it properly and we ignore the competing risks. One of the first things that you should see is that we can end up calculating a negative probability if we use the wrong method, whereas if we use the correct method, we'll always have a probability between 0 and 1. But what you should notice is that these two methods, so long as the probability of remaining in the state is close to 1, these two methods give pretty much identical results. And if I actually zoom in on that part of the graph, you'll see it's pretty impossible to distinguish the probabilities when you're up in that area where the probability of remaining in the state is 0.95 or higher. So that's why I had that rule of thumb earlier. And you'll see that when we choose a cycle length of 1/12, in this case, we're nearly always going to be up in that region. It's quite a low chance of us ending up down here. Whereas with the longer cycle lengths, the kind of teal and violet dots are all down here, which are where you've got a big error in the calculations. So to conclude, you should pick a sufficiently short cycle length that it is believable no more than one event could occur, and also that picking an even shorter cycle length would not make a difference to your results. It can be helpful to pick a cycle length that aligns with treatment schedules. If you pick a suitably short cycle length, it won't make a big difference whether you calculate transition probabilities, adjusting for competing risks or not.